determining the polarity of bonds and of molecules. All right, first thing is that electronegativity defines the degree to which electrons are shared between two different elements within a bond. So as an example, between hydrogen and fluorine, within hydrogen fluoride, the electrons are actually going to be going more towards fluorine than hydrogen. Fluorine has an electronegativity of 4.0, and hydrogen has an electronegativity of 2.2. Now, electronegativity defines how much the electrons are dragged towards it. Fluorine has a higher value, hence electrons are dragged towards it. And so fluorine, dragging these negatively charged electrons towards it, is going to get a relative negative charge. Hydrogen, losing some of this electron density, will get a relative positive charge. We can say that there are two poles here, a relatively positive pole and a relatively negative pole around this bond. We can say that this bond is polar. It's a polar covalent bond. This is what you get when you have an electronegativity difference between two elements of between 0.4 and 2.0. If there's an example like chlorine molecule, where both elements have the exact same electronegativity, 3.0, when there's no difference in electronegativity between them, then electrons are going to be shared equally between the two elements, and hence there should be no overall positive and negative end. Hence, there is no series of two poles. There is no dipole, and hence you call it a nonpolar covalent bond if there's no difference between the elements or a very small difference between them, 0.0 to 0.4 in electronegativity. And if there's a very large difference, like between lithium and fluoride, between this metal and this nonmetal, you actually say that you have, having this very large difference, you have a very, very significant pull of electrons towards the more electronegative atom, so that the electron is actually given to the more electronegative atom and lost from the less electronegative element. And so you get an ionic bond if the difference between the two elements is greater than 2.0. So these are bonds, but we also need to consider whether molecules are polar. Now, ultimately, molecules are polar if two ends of them are poles, if one end of it is negative and one end of it is positive. But you can also consider whether the dipoles, those arrows that we draw, cancel out. If they cancel out, then you'll have no ends which will be relatively positive versus other ends which are relatively negative. Hence, the molecule will be nonpolar. Or if the arrows don't cancel up, if they add up to other arrows, then you get a polar molecule, presuming that you had polar bonds. Presuming polar bonds. Or if the arrows don't work out for you, particularly for the three-dimensional problems, the more complex ones, you could ask yourself, are all sides around the central atom the same? If all the sides are the same around the central atom, it's a nonpolar molecule. If they're not all the same, then it's a polar molecule. So, to consider all this, you need to be considering molecular geometry. So, to get to the polarity of the molecule, you need to first draw out the Lewis dot structure. This will give you a code about the number of bonded atoms and the number of lone pairs on the central atom. This code tells you the molecular geometry and therefore the polarity of your molecules. So combine your molecular geometry with the polarity of the bonds, and that tells you the polarity of the molecule. So let's look at HF. All right, so we have a polar bond here between H and F. We draw the arrow towards the fluorine, the more electronegative element. Now, is this arrow canceled out by any other arrows? No, this is the only arrow. Hence, there is an overall shift of electron density towards the chlorine and away from the hydrogen. Hence, we have a polar bond here, and we also have a polar molecule. Polar bond and polar molecule. Because the arrow is not canceled out. Because not all the sides are the same. Because there's a positive end and a negative end on this molecule. How about carbon dioxide? Carbon, it's an electronegativity of 2.5, oxygen 3.5, so electron density goes towards the oxygen. Now, do we have polar bonds? Yes. Do we have a polar molecule? Well, let's see. What you need to do is add up the bonds, or the dipoles here. So we have one which goes exactly to the left, and there's another equal magnitude one which goes exactly to the right. These cancel each other out. They cancel each other out. There is no one end of the molecule which is relatively positive and one end which is relatively negative. Instead, both ends are relatively negative. And so there is no overall two poles. This is a non-polar molecule. Another way to know this is on the central atom, those two oxygens are the same. If everything around the central atom is the same, then you have a nonpolar molecule. Next, sulfur dioxide. All right, so this is the Lewis dot structure of sulfur dioxide, but you're interested in more than just the Lewis dot structure. You need to get to the molecular geometry. Then the arrows, that gives you the polarity of the molecule. So, though this is your Lewis dot structure, this is not actually how the molecule will arrange itself. You see, it has two bonded atoms on the central atom. It has one lone pair of electrons on that central atom. So code of 2, 1, that actually gives you a bend structure, or a V-shaped. So you get the following. Lone pairs of electrons gets its own space, just like these bonded atoms. And so now we can consider the arrows. Now oxygen is more electronegative, and so the arrows will go towards it. So we see that we have these two arrows. Do they cancel out? Well, kind of. You see, these arrows, they have components or parts. This arrow has a left part and a down part. This arrow has a right part and a down part. Now, the left part and the right part, when we add them up, they will cancel. But what about these down parts? Well, they actually add up to a bigger down. There is an overall dipole, an overall arrow. We signify this using this cross. So we have an overall molecular dipole. Hence, we have a polar molecule. Here we have polar bonds and we have a polar molecule. It's polar even though the Lewis dot structure looks a lot like carbon, because the molecule is actually bent. You must pay attention to molecular geometry. This is why we care about it. Next, boron trichloride. Alright, so chlorine is much more electronegative than boron. We draw the arrows towards it. But wait, we shouldn't even consider arrows until we've gotten into the molecular geometry. Alright, so what is the molecular geometry? Well, there's 1, 2, 3 bonded atoms on the central atom. There's 0 lone pairs on the central atom. So 3, 0, that is a trigonal planar structure. In fact, this one Lewis dot structure is actually the same as the molecular geometry. So we can now consider this Lewis dot structure because it is the same as the molecular geometry. So draw the arrows towards the more electronegative elements. Now, it turns out that these arrows are going to cancel. They have parts. This arrow has a to the left part and a down part. This one has a to the right part and a down part. And this one has just a part. Now you can see that the left part and the right part will cancel. And these two down parts, each of them is half the magnitude of this up part. And so these two down parts combine to equal this up part. So up and down part cancel. There is no overall dipole. Hence, non-polar molecule. Now, if you're uncomfortable dealing with this, you could just say, are all things around the central atom the same? Yes, here we have 3 chlorines. And, therefore, the molecule is nonpolar. Next, CF4. Here's the Lewis dot structure. Now draw out the molecule in its molecular geometry. We have 1, 2, 3, 4 bonded atoms. We have 0 lone pairs on the central atom. Hence, we get the following structure. In 3 dimensions, this is a tetrahedral structure. Now, we see that the arrows are a little bit more complex in this case because they're in 3 dimensions. So, you could consider that they have parts. This one has a down into the left part. This one has a to the right part, a down part, and it goes into the board. This one has a down part to the right part, and it actually goes out of the board, and this one just goes up. Turns out that these are all going to cancel. How can you quickly know that they're all going to cancel? Well, all the things around the central atom are the same. Hence, there's relative symmetry in each of the axes for the dipole. Hence, nonpolar molecule. All the same around the central atom, nonpolar molecule. Try this one. NF3. All the same around the central atom? Well, this is the molecular geometry. Is everything the same around the central atom? Well, actually, no. Because one of these is a lone pair. This is different than all the fluorines. We have polar bonds. All of them go down in some direction. Hence, there is an overall dipole downwards. This is a polar molecule. Finally, C2H4. Oh wow, none of these bonds are polar. They're all nonpolar covalent bonds. Hence, if all you have is nonpolar bonds, you must have a nonpolar molecule as well. Recognize that C and H together, anytime it's just carbon and hydrogen, is nonpolar bonds and nonpolar molecule. Thanks for watching.